Thank you, both people here in person and virtually, for spending some time with me. There is a Slack channel specifically for this talk. If any questions come up as I'm talking about things, please feel free to type them into Slack. I probably won't have time at the end of the talk to talk about them from up here, but I will answer whatever you want to put in there about anything related to this. So my talk for you today is called Game Development in 8 Bits. The subtitle for today's talk is Stupid NES Tricks. I use that name intentionally. Before I jump in, there are, I think, two initial questions we should get clarified. First off, what is NES, for anyone who is not familiar with this? These letters indicate the Nintendo Entertainment System. It is a home video game console produced by Nintendo, shocking, I know, released in the US in October 1985. So this system is now 36 years old. The Nintendo Entertainment System was the American redesign of Nintendo's Japanese home video game console, the Family Computer, or Famicom, which came out 2 years earlier, 1983. The US NES was internally the same exact hardware, but the outside was redesigned to make it look less like a toy and more like a VCR. True story. Both of these systems, Nintendo R&D, they were given the guideline for their design that at a baseline, the system needed to be able to play a decent home version of Nintendo's hit arcade game Donkey Kong, which came out in 1981. Worldwide Smash really kind of put Nintendo on the map for a lot of people. You can see the way Donkey Kong works. There's a lot of animation, it has a lot of color. Generally a pretty good looking game, definitely dated. But to put into context how big of an achievement Donkey Kong is, the predecessor home video game console was the Atari Video Computer System, or 2600. Released in 1977, has this beautiful wood grain front panel, has these joysticks that only have one action button on them, and the game that the Atari 2600 was built to play as a baseline was this game called Combat. 2 players, they each control one of these little tanks moving through a play field of these kind of walls and shooting at each other and spinning around really fast when they get hit. This is the game the 2600 was built to play, and I think Donkey Kong is kind of leaps and bounds beyond this. So inside that console, the NES features an MOS Technologies 6502 CPU, very popular chip, actually came out in 1975, 10 years before the NES did, running for, at the time, a blazing fast 1.79 megahertz. It also features a custom Ricoh designed and manufactured picture processing unit, or PPU. This is kind of like the graphics card of the NES. This enables the NES to do 256 by 240 pixels screen resolution, and it lets it show 64 colors. The NES also has 2 kilobytes of system RAM. It has 2 kilobytes of video RAM. That's all the memory you get inside the system. It has no permanent storage of any kind. It has no operating system. It has no hardware clock. There is nothing. Everything the NES is going to run comes off of the cartridge that you put into it, which gives you space for 32 kilobytes of actual game code and 8 kilobytes of graphics data. So your whole game is going to fit into 40 kilobytes. The second question we should get out of the way is, what exactly does 8-bit mean? Kind of important. The bit, if you are unaware, is a binary digit. So 1 bit represents a 0 or a 1, an off or an on. It has 2 possible values. And if you combine more bits together, you can represent a broader range of things. So if you have 2 bits, that gives you 4 possible values. If you have 4 bits, you can do 16. And on and on. And when you get to 8 bits, this has a special name. We call that a byte. And a single byte lets you represent 256 different possible values. What makes the NES or other systems like it an 8-bit computer is that it processes data 8 bits at a time. Or to put that another way, as far as the NES is concerned, everything in the entire universe is ultimately represented by a number between 0 and 255. We're going to see these numbers all the time. So with that out of the way, let's dive in. I'm going to start by talking about drawing graphics, a very important thing for a video game system to do. The NES, as I mentioned, has a screen resolution of 256 by 240 pixels. If I multiply those two together, we get 61,440 pixels in every screen of graphics. And because of the way the NES handles color, if we were to do things this way, you could fit 4 pixels in a byte. So that means you would need about 15 kilobytes to store a single screen of graphics. And that is a problem because the NES has 2 kilobytes of video RAM. So you would not be able to display a screen. You can't fit it in memory. So the first problem we need to talk about is how do you draw a big screen full of graphics when you only have 2 kilobytes to work with? For the NES and for many other game systems of its time, the answer is really you get kind of abstract. You don't draw with pixels because you can't. The hardware just isn't powerful enough to do it. So instead you draw with tiles. Tiles for the NES are generally 8 pixels by 8 pixels square. And those tiles live in what is called a pattern table. So the 8 kilobytes of graphics data that you have is enough storage space for you to fit 2 pattern tables for your game. And each pattern table holds 256 tiles. There's that number again. Literally everything that your game will ever draw to the screen must be located in one of these 2 pattern tables. If your game wants to draw text to the screen, you need to include a font as some of your 512 tiles that you have access to. These are the pattern tables from Super Mario Brothers for the NES. Literally everything Super Mario Brothers will ever draw to the screen is right here. We also get a little bit more abstract by using layers. So here is a screen from Super Mario Brothers. What is actually happening here is we've got 2 layers superimposed over the top of each other. We have a background layer on the left, which is for things that are not really going to move around a whole lot. The background layer can scroll left or right or up and down, but the tiles in the background are locked into a grid. You can't just put them anywhere. The sprites, meanwhile, are for things that are going to move around a lot. That's usually where you see your player character, enemy characters, things like that. Much more limited because sprites can be put anywhere down to the pixel. So I'm going to start by talking about backgrounds. So as I mentioned, it's a grid. It's 32 tiles wide. It's 30 tiles tall. Multiply that together, you've got 960 tiles in a screen. And you need 1 byte for every tile, because you need to know which tile from 0 to 255 goes in that slot in the grid. So you can fit an entire background in 960 bytes, because you only need to reference the tiles, not individual pixels. You actually have enough space to hold 2 screens in memory at the same time by doing it this way. As far as the sprites are concerned, they're handled a little bit differently. You get 256 bytes of RAM just for sprites, and it takes 4 bytes to store a single sprite tile, because you need to know the X and Y position on the screen exactly of where that sprite's going to go. So you divide that out, you can have 64 sprites on screen at one time, which sounds pretty big, but 8 by 8 pixels is very small. So like small Mario here is actually 4 sprite tiles working together to show you a single image. Technically, you can have 64 sprites. In reality, you're probably going to have a far smaller number of actual objects moving around. That's how we handle a single screen. Single screens work for Donkey Kong. It doesn't have to scroll or do anything, but a lot of NES games do. A popular one is Super Mario Brothers. I apologize if I feel like it's the only thing I'm talking about. I swear there will be other things. This is World 1-1. This is the first stage of Super Mario Brothers. It is 14 screens in length. So we need 14 screens of graphics. It's 960 bytes per background. That's about 13 kilobytes of level data that we have to encode somewhere. We get 32K to store all of our game code, which means you can fit your 13K and still have plenty of room left over for like what happens when I press buttons on the controller and things like that. But that's just the first stage. Here it is again. We also need to worry about 1-2, 1-3, 1-4, 2-1, 2-2, 2-3, 2-4, And then we have to do that 4 more times because Super Mario Brothers has 32 stages, and they are all 10 plus screens in length. So you got a big game. How do you fit that into 32K? Because Super Mario Brothers is only 32K of game code. The answer, unsurprisingly, is you get even more abstract than we already have. One way to do this is you use these kind of repeated meta objects in your backgrounds. This is a screen from the Metal Man stage of Mega Man 2. There's a lot going on here, but really all that's happening is you've got these 3 blocks on the right side, which are each 2 by 2 tiles, and the whole background is just those 3 blocks repeated. So we've gone even another layer beyond, from pixels to tiles to now multi-tile things. You can use a kind of basic compression. For the NES, it's not very powerful on the math front. So compression for the NES is usually some kind of run length encoding. Something like, I've got this thing that's going to repeat a certain number of times, and then I've got like a very tight little for loop kind of thing that can just draw that thing repeatedly into video RAM. In the case of Super Mario Brothers, we get even further beyond. Super Mario Brothers features what people who have analyzed the code like to call set decoration. So here you've got 3 screens arranged left to right. These 3 screens repeat endlessly in the background of many stages. So take a moment, notice the pattern of clouds in the sky, notice the pattern of the hills and bushes on the ground. So as you start looking at Super Mario Brothers, you start seeing, here's 6 screens in a row from that first stage, and those clouds repeat in a pattern, and those hills and bushes repeat in a pattern. What set decoration allows Super Mario Brothers to do is the only level data you actually need to store is what are the things that are different from that set decoration. You only need to store the things that get laid on top of it. So Super Mario Brothers stores World 1.1 in 101 bytes. It is tiny compared to the 13 kilobytes we talked about before. The code has a header and a footer, which tells the game where the level data starts and ends. And then in the middle, it has these pairs of bytes. And each pair is a location on screen and what to draw there. So the first pair, 07, says go to column 0, row 7 of the screen, and then draw. 81 says draw a question mark block that has a coin in it. Or go to column 4, row 7, and draw a row of 4 bricks. It's a very compact format, which is how you're able to fit 32 stages into a very small amount of space. So that's graphics. Let's move on to physics. Jumping. Stuff like that. So back to the Atari 2600. I think the most good-looking, technically impressive game for the Atari 2600 is probably Pitfall. Looks pretty good for an Atari 2600 game. The main thing to notice, though, is our hero, I believe he's called Pitfall Harry. He runs at a constant speed. He has a jump, but it doesn't really feel like a real jump. He kind of does this weightless sort of float thing. And this came out in 1982. So you go 3 years later when Super Mario Brothers comes out, and Mario has weight. He accelerates smoothly over time. He's not just always in a run. If you are moving in one direction and then you turn around to go the other way, he skids to a stop before he starts moving in the other direction. One of the things that made this game really impressive for its time was that Mario has a feeling of weight when you play with him. What makes this interesting is the 6502 is not really known for math. It can do 4 math operations. It can do addition, subtraction, and it can do these bit shifts left and right, which are basically multiply and divide by 2. And anything that is not in this list that you want to do, you need to write a function or a subroutine that does that. You want to multiply by 3, you need to write a function that multiplies by 3 in terms of addition and subtraction and bit shifts. And physics-type equations usually need more than just adding and subtracting. So how do you get that kind of physics feel when you don't have any of the math power to do it the real way? Super Mario Brothers, many other games like it, fake it, unsurprisingly. You may have heard of floating point numbers, or floats, where you can have any number of digits on the left or right of the decimal point. For Super Mario Brothers, they use fixed point fractions, and they call them 8.8 because you've got 8 bits on the left, you've got 8 bits on the right, and that's all you can use. Basically, they just track every position using 2 bytes. The first byte is like that left byte, and that's your actual on-screen pixel position for where Mario is going to be drawn. And the second byte is a subpixel. You use it to represent like a fraction of a real pixel. You could have anything in like 1/256th of a pixel. Super Mario Brothers doesn't even care about all that. It just uses multiples of 16, which is enough to give them like a resolution of 1/16th of a pixel for how fast things are moving, where on screen things are located, anything like that. And using this relatively simple system gives them that smooth acceleration curve because you can add fractions of a pixel every frame and get something that looks like a realistic movement. Before I leave physics, we should talk a little bit more about collision detection, also an important thing for many games to do. And I think the best game to talk about collision detection with is probably Contra. It was an NES port of a popular Konami arcade game. The box art is a complete and total ripoff of late 80s Arnold Schwarzenegger, Sylvester Stallone action movies, including featuring like the character from Alien in the middle. Notably for the NES, it allows for 2-player simultaneous play. So each player can have their own controller and they can be on screen doing stuff together at the same time. Contra is a game that moves very fast. So there's a lot of things running around the screen. There's a lot of bullets flying all over the place. And each of these things need to have collision detection because you need to know, did a bullet hit an enemy? Did an enemy bullet hit the player? Like, lots of things need to be checked against each other. One of the other things that makes this difficult is there's just a wide variety of shapes. So the player character can be standing up in a vertical position. They can be lying down flat on the ground. They can be jumping, which makes them like a little round shape. The enemies also come in a wide variety of shapes and sizes. So if you're going to do these comparisons against each other, the bounding boxes you would normally use to detect a collision are going to constantly be changing, which for a system that can only do addition and subtraction is challenging. So to show you like the extreme level of this, this is a boss fight from about halfway through the game that's being done in 2-player. The players together have managed to put 11 bullets on screen at the same time. Those are those little white arrows. There are 4 possible enemy positions that they could hit with those bullets, which are the little gold arrows. So every frame of graphics, because Contra is running at 60 frames a second, we need to check all 11 bullets against all 4 enemies, and then we need to check all 4 enemies against both players separately, which is a lot of work to do in 16 milliseconds. So how do you do this when you've got lots of objects and you need to do this in real time? The developers of Contra came up with a really interesting solution. They decided that the fastest way to do collision detection is point versus rectangle. So one thing is represented by a single point, the other one is a rectangle, and you just check, is this point inside the rectangle? If it is, collision, we're good. And they decided to make the player always, always, always be the point, no matter what. So here you can see 3 different collision detection scenarios, and there's a little green dot with a green circle around it. That is the point that represents the player for collision detection. And there's this little white plus sign shaped thing that is an enemy bullet that we're going to do a collision detection with. And what they did is the player is always the point, the enemy is always the rectangle, and the rectangle changes based on what position the player is in. So all you need to store for your enemies is like what is the offset of the box relative to where the enemy actually is, and then it just changes with the player shape, and it lets you do this really pretty fast. I think it's a good time to talk about random numbers. Less games need random numbers than you might think. Most NES games, most games in general until relatively recently, are very deterministic, where like things are laid out in a particular way, and how you press buttons on the controller ultimately is what affects what happens, not any sense of randomness. But there are games that need random numbers. Puzzle games, Tetris, lives or dies by its random numbers, because literally the entire game is you don't know what piece is going to come next, and you have to figure out how to deal with it. Role-playing games like Final Fantasy need good random numbers because they're kind of simulating dice rolls all the time. So you're walking around, do you end up fighting some monsters randomly? If you do, what monsters are there? Who do they try to hit? Do they actually hit them? How much damage do they do? All these calculations that you need to do with random numbers all the time. So in any kind of modern language, the way you would do this is you've got some kind of system library call that lets you get a random number from some source of randomness. So if you're using JavaScript, you call math.random and you multiply and floor, and that gives you a random number between 0 and 255, which is cool. The NES doesn't have a random number generator. It doesn't have anything built into the system. So if your game needs random numbers, you need to come up with your own method of generating random numbers, and every game kind of does it differently. So the next problem we have is, how do you do that? I'm going to show you 3 approaches. I have ordered these 3 approaches in order from least to most stupid. The best one, probably, is Tetris. Not really surprising. Tetris does it with math, which is probably the way you should do it. They use this construct called a 16-bit Fibonacci linear feedback shift register, which is a complicated way of saying you have 2 bytes of memory, you do these weird bit-to-bit comparisons within your 2 bytes, and then you shift things around in particular ways. And that gives you a fairly convincing stream of pseudo-random numbers. Final Fantasy takes a different approach. Final Fantasy, if you've ever played it, there's this great bit relatively early in the game where you cross a bridge and you get this cutscene, which is amazing for the time, where it tells you your heroes are going on this amazing quest, et cetera, et cetera. And at one point it says, programmed by Nasser. And as a kid, I was playing this, I was like, oh, this must be like some company that they subcontracted out to. No, it turns out Nasser is actually Nasser Gebeli. It's this guy who emigrated from Iran to Japan and then was hired by Squaresoft as a contractor. And he wrote the entirety of Final Fantasy's game code all by himself. He was very busy. He needed a way to get random numbers. And so he did what anyone would do, and he hard-coded a table of 256 pre-computed random numbers. So Final Fantasy has this table in its game code, and then it has 1 byte that it uses as a pointer into this table. And every time Final Fantasy needs a random number, it bumps the pointer up by 1 and looks up the next number out of the table. Which sounds really dumb. But it kind of works. Like, I've never played Final Fantasy before and been like, oh, like, this is just looking up numbers out of a table. Who wants that? So that's approach number 2. And approach number 3 is actually from Contra, believe it or not. Contra needs random numbers to determine when to randomly spawn these soldier enemies that run in from the left and right sides of the screen. It's not like a huge use of random numbers. If things go badly, you're not really going to notice. So Contra has the stupidest approach of all. Contra's approach is there is 1 byte of memory that stores your current random number. And when Contra is not busy doing something else, like collision detection, it figures out the current frame number, and it adds that into the random byte as fast as it possibly can, until the next frame of graphics starts, and then it stops, and that's your random number. So if you're currently on frame 7 of graphics, it's just gonna add 7 over and over and over and over again until it needs to do something else. And then wherever it stops is the number that you get, which is the worst random number generator sequence of any of these that I've shown you. And again, for Contra, it works. Like, eventually, you see enemies running in and out, and you really don't think about it. One more thing to talk about is how you save your game. Frequent thing that I have yelled at people when I was playing NES games that did not have good saving mechanisms. When these games were in the arcade, like if you go to play Donkey Kong in the arcade, The expectation is your game session is not going to last very long. If you can play 5 minutes of Donkey Kong on a single quarter, you're halfway decent. Like, that's good. But as these games move into the home, those expectations change, because now people are putting in a huge chunk of money up front for a game that they are going to be stuck with forever, unless they sell it or something. But people start expecting a lot more out of their games. They want something that they feel is going to be worth their money, where they can get a lot of time and enjoyment out of things. And so you start seeing games where it's not just a simple, tight little arcade loop. It's like bigger, broader, more expansive stories. The problem is you are on a read-only cartridge. You don't have any way to write your game data anywhere. So early NES games, they try to get around this with passwords. Good example, Mega Man 2 uses this kind of system where there's a grid. You put these little red balls in the grid, and that lets you pick up where you left off. So every time you finish a stage, it will display to you this grid, and you can pull out your notebook, and you can hand draw, here's the grid, here's where everything goes, and then get back to it. This system is very simple. It always uses 9 of these red balls, and they are just a literal 1-to-1 ratio of is each boss alive or dead, and how many of these energy tanks that you can pick up only once have you picked up during the game. If you play enough games of Mega Man 2 and you write down enough of these passwords, you can eventually figure it out and just make your own password for whatever you want. An alternative approach is Punch-Out. Punch-Out, you get a password which is 10 digits. It's basically a phone number. It's set up 334 even. Nintendo really, really did not want you to reverse engineer this password system. They were like, I don't want anyone coming and being like, okay, I figured it out. I just put in this number, and that gets me exactly where I want. Punch-Out has a fiendishly complicated password system where it takes all the data about what you've done so far in the game, stores those into particular bytes, and then scrambles them around and mangles them with each other to end up at a password. There's a great article here that goes into way more depth than I have time for. Surprisingly, Dragon Quest II, a big, long RPG, playing this game takes you like 30 to 40 hours, and you are not going to just keep the system on the entire time until that is done. It needs to save data about this giant world, and you have 3 different characters who each have their own stats. There's a lot of stuff to keep track of. In Japan, Dragon Quest II uses passwords. So whenever you go to save your game, it gives you what is essentially a poem that you, again, copy down into a notebook somewhere, and then you come back and you type in the poem using this grid, which if you've ever tried to like search for a movie on Netflix using your remote control is maddening. People don't like these password systems. They want something better. So Nintendo says, okay, how about we come up with an alternative? The original alternative they come up with is called the Famicom Disk System. It comes out in Japan in 1986. It is this giant red box, which is a disk drive that sits underneath your Famicom. And they start selling games for it that come on these disks. And they're writable disks that are bigger than a game cartridge. So you can fit something like 120 kilobytes or something like that on one of these disks, and they're writable. So you can save your game anywhere and just write as much data as you want. They have this little tab at the bottom that says Nintendo. Then, as now, Nintendo is paranoid about copy protection. So this little tab at the bottom, the I and one of the N's are actually physically indented into the plastic. And inside the drive, there's a metal plate that has a little I and a little N that need to fit into those depressions. And if the plate doesn't fit just right, it refuses to play the game. It's like, clearly you are doing something shady. The problem for Nintendo is that they chose a disk format that was in common use at the time. It was called the Mitsumi Quick Disk. Didn't really see a lot of release in the US, but in Japan it was popular for things like word processors or like early computers of the day. 2.8-inch disks, here they are with a save icon for size reference. You could buy these. You could just go to a store and buy some quick disks. And it did not take long for Japanese players to figure out that with a little home modification, you could turn these quick disks into something that the disk system would read as a real game. It got so bad that by the end of 1986, you had companies that were literally putting out disks that already had those little indentations in them because they knew what you were trying to do. Nintendo did not like this. Shocker. So they went back to the drawing board. How do you allow people to save their game data when you don't want them to copy it? So they went back to cartridges. They came up with, there's a new little chip here called the MMC1, which allows you to slap on a battery and another chip full of RAM. And that battery just gives you a little trickle of electricity that keeps the contents of the RAM alive even when it's not in your system. So now you've got an extra 8 kilobytes that you can just write whatever you want to. Which leads us to another problem. You start seeing this like in game manuals or in actual games themselves. You'll see things where it's like, hold in the reset button as you turn the power off. Very important. You will destroy your game if you don't do this. What is going on with this? Well, it turns out when you turn off the power to your NES, it doesn't just go from on to off immediately. What actually happens is you turn off the power, and the processor still has a little bit of residual electricity in it, and that just fades away relatively quickly, but it's enough time that like the processor is still running. And as the processor has less and less electricity available to it, it starts acting more and more erratic. So it's unlikely, but it is possible that as you turn off your system, that processor is going to do something totally unpredictable and write data into that save RAM and just corrupt everything that you've put there. So you start seeing these warnings because holding the reset button puts that processor into a very tight little loop where it can't break out and do something else. But if you're a game developer, you don't know that your player actually did this. You don't know if the RAM has been messed with or not. So how do you do that? Because you want to load the save data, but you also don't want to load something that's been turned into garbage. Dragon Warrior, the US release of Dragon Quest I, did a really interesting thing where they just write the save file many, many times. So I think they make something like 8 copies of your save into that save RAM. And they write a little checksum with each of those. So when Dragon Warrior goes to load your save game, it reads the first one, it checks the checksum, and if they match, cool, it will load your game. If they don't, it just goes to the next one, and the next one, and the next one. And if it goes through all of them, and all of them are bad, then it just shows you like the standard title screen that says start a new game. But this is how it gets around that like, did you hold the reset button or not problem. So I've been up here talking to you for about half an hour now. You may be wondering, what is the point of all of this? Why are you rambling at us about these old games? There are a number of reasons, but I think the one that really kind of sticks out to me is doing all this research, learning all these things about all these old games has shown me that there is value in embracing the stupid. What I mean by that is, you can have a problem that you need to solve, and you can come up with a really dumb solution to it that does what you need to do. And that's fine. There is nothing wrong with that. Eventually, you might find a situation that proves to you that your situation is too dumb, and it doesn't solve everything you need to do. And at that point, you can go back, and you can change it. But up to that point, just get things done, ship them out the door, who cares? I would rather hard code a table of 256 random numbers and ship Final Fantasy than sit there for months trying to figure out the perfect random number generating algorithm. That's my takeaway. You may have your own. That's the bulk of what I've got. If this is something that you are interested in, if you want to know more about how the NES works, developing for it, anything like that, I'm going to show you some resources. One I will definitely point to is Nathan Altus's book, I Am Error, from 2015. This is part of an MIT Press book series called Platform Studies. The whole series is great. This book in particular goes into the design decisions that led to the NES in the state it was actually released in. Fantastic book. This is the book that got me into doing this in the first place. If you want to drink from the fire hose, there is the NES Dev Wiki. There is a community of people who still make NES games to this day, brand new games that you can buy on hardware and play in an actual NES console. The NES Dev Wiki is like the central place for information about everything about how the NES works. If you want to start writing your own code, this is actually my site. I've been working on a tutorial series / book kind of thing for a couple of years now. I will walk you through how to make NES games in assembly. And my only assumption is that you have worked in some kind of programming language before. JavaScript, Python, Ruby, whatever, it does not matter. Like, you know what a variable is and what a for loop is. That's all you need. Eternally in progress, but there is enough here that like you can get a super solid introduction to go look at other people's code and understand what's going on. And that's basically it. So thank you again, all of you. Please stay in touch. Please stay in touch. This is my email address if you want to get in touch with me. There is also, as I mentioned, there is a Slack chat room just for this talk. If you have any questions, post them there. I'll be answering them for as long as I'm able to. So the question was, Final Fantasy has the table of random numbers. How do you not get the same game every single time? The initial seed pointer into the table, I think, is based on something like how many frames you wait before you press start at the title screen. So if you use something like an emulator where you have save states, you can save a state of the game and reload it, and every single time you'll be like, okay, I know I am 7 steps away from getting into a fight, and this is exactly what is going to happen every single time. But it's that from startup, when you first hit that power button, that's how it seeds that number. You can. I simplified a little bit there, but as far as like the NES hardware is concerned, it just knows there are 2 pattern tables. One is sprites, one is backgrounds. Chips like that MMC1 that enables you to do saving let you put in more than 8 kilobytes of graphics data. You can only expose 8 kilobytes to the system at a time, but you can like change which 8 kilobytes it's seeing. There are also later chips that enabled you to set up, instead of CHR-ROM, where it's like baked in, you could do CHR-RAM, where you could literally just write in real time what goes into those pattern tables. There are games like Battletoads or Metal Storm that use that to do these really complicated parallax effects because they're constantly redrawing what is in the tiles while you're playing. You can, to some degree. There is a decently sized community of people who use C to write NES games. There's basically a C library that you use the functions in the C library, and then it can compile down into 6502 assembly. There's a guy named Douglas Fraker, I believe, who has like a whole tutorial series on C development for the NES. I heard about that one recently. I have not had a chance to poke around. I don't think I am the person to give the talk about that, but it sounds super cool. Yeah. Someone asked, how does the Game Genie work? The Game Genie literally just kind of intercepts in between the cartridge and the system, and it allows you to like overwrite RAM values. So like the cartridge code will say, hey, do this to the RAM inside the NES, and the Game Genie will intercept that message and actually set it to something else instead. Game Genie has its own complicated password system of how the password you type in turns into like what to do to a particular RAM address. How long until the RAM battery dies? Really depends. I'm not sure. I own some NES games that, as far as I know, still have the original battery in them and work just fine. Other people, they definitely die. It's kind of hit or miss. Okay, and then I've got one other question here. Shouldn't the random number multiply by 256? I believe this is about Final Fantasy. I'm not entirely sure what the question is.
It's the JavaScript.
Oh, the JavaScript one. Possibly. I might have done that wrong, in which case, thank you for pointing that out. All right, it looks like I am at time. So, like I said, I will take a look in Slack. I'll try to respond to everyone who has a question, and if not, please stay in touch. Thanks.